Aber kurz wissen.
Course to quantum field theory. One or introduction to quantum field theory. I'm very excited for several reasons. First, this is my first time teaching this course. And second, to see so many of you. I saw that there are about 40 people enrolled, which is already a lot. And then some don't have access to Moodle. I just overheard. You can, even if you're not a student, sign up for this Moodle as an external person, and then you can access this page. You don't have to ask for help. So Moodle, we'll use it as a platform to communicate. If you haven't enrolled, please do so. You find the lecture notes right there. Then you've seen I pushed the record button. This is a conference video system thing, and I'm misusing it for recording the lecture because there are people abroad. Where am I? Hello, France. Yes, at least one is watching from France. So I'm recording this, but then to do this, I actually have to use Zoom. Maybe it's easier, but I'm using Zoom. So this is also broadcast if you want it. I'm not inviting you to stay home and watch from there because it's much more fun here to interact, but it's a byproduct. So the lectures after they've been recorded will show up here. I hope it works. I tried it once. The audio was not perfect. Another reason to come, but let's see. And you find the problem sets. How are we going to go about it? Let's talk about the exercise classes. So there will be 2 lectures and 1 exercise class per week. And the first was there's a collision between our exercise class, days 11 to 1, and the lecture in condensed metaphysics by Professor Brax. And so we have started a little survey who can make it win, and many of you have answered. How many? Well, I don't know. So the preferred date according to this survey is the Wednesday, same time, but 1 day later. Here there are 10 and there are 15. So I would shift it there. I assume that there will be some in this group cannot make it there. And I'm very sorry. Like thinking collectively to optimize our success is to pick the date where most people can. I really want to make it work for everyone, but it's just not possible. So all I can do is maximize it for most people. This means individuals will be really, really sad. I think we shifted there. Not everybody has voted yet, but I think the people who care the most about the course have voted, right? So we'll move the exercise classes to Wednesday, 11 to 13. But, okay, so talk about exercises. Case Haddad is going to teach those exercise classes. He kindly offered, and I warned him, don't do it, to talk to you privately if you can't really make it on these days. Just see him at some other point, talk to him, and then you'll find some. He's happy to answer questions. And the warning was, okay, I suppose you might take him up on this offer. And that results in lots of work. But let's see how it goes. So there's a chance. Ask all your questions. Yes?
Ist der neu an der HU, ist der Kurs nicht einschreibgeschützt? Also man braucht doch so einen Schlüssel, um sich in den Moodle-Kurs
Yes.
Frag mich immer, wo alle anderen den schon
Agnes, you probably have you been able to, I'm not sure how this works. Can you register on Agnes? This is sort of, yes. Then if you have done this a little bit before the course started, then you have received an email with that keyword.
Okay.
If you don't, it is learning QFT.
Okay.
Learning like this, capital L, and then QFT, no space, and QFT capitalized. That's okay, gets you into the Moodle course.
And so, will be exercise to be recorded as well?
I don't no, because people are more reluctant to talk and participate and come forward when they're recorded. I would be. So that should really be a place where there's lots of interaction and going around and working in groups, and there's no point in recording the blackboard. The actions happening there. It won't be like the lecture where someone writes down all the solutions. You will get sample solutions, so you can look at them carefully, and the exercise here should be for discussion, but they won't be recorded. Look at that. So you have 1 week to solve them. See how they look. That's the first problem set. Always close to the lecture course. Well, maybe I should tell you what we're doing here. The first will be an appetizer. I thought I'd start easy. Like a gentle introduction, because not everybody will be here the first week. Although I hope everybody's here because there's no room. So we'll start with relativistic quantum mechanics. I'll give the introduction soon, but since I open this up, so it's quantum mechanics and trying to make this relativistic. And then you have 2 problems. There's lots of explanation. It's less bad than it looks. And then you run this up and you submit it via this link. So that's now you can upload it. All right. And it's due on Wednesday evening. So then with the Thursday morning, like this, we'll start a new week and new topic, and so it's due then. And the exercise classes, since they've shifted to Wednesday now, well, you can ask about the problems. If there's still something that you haven't solved yet, then you can discuss these remaining questions in those classes and everything else. And maybe during the day, finish these problems. They won't be graded super rigorously. It's more like, have you put any effort in it or not? If it's all wrong, but you tried really hard, it scores 100%. Because the exercises are for learning, right? It'll be different for the exam at the end. Right? Not sincere, it's just as good as if you had nothing, but here you're supposed to write something and try and then learn from it. Right now it's set up that everybody uploads their own solution. That's a lot of people, and a lot of grading. Okay, so we'll probably have to have group work, but this is not set up for it yet. So I'll have an activity where you pick your group, and then so that Moodle can actually record whose points are these. So he'll give you out of 100%. It's more like an estimate. It's very often you should have 50% roundabout there at the end of the course to get the Übungsschein. And since we can't resolve individual percentages, if you have 48%, that's passing as well. Right? It's not very strict. That's the structure. So we start with this stuff. Yeah. Okay, so Case, do you want to say hi or something? One second, I don't think I switched this
Can you hear me at this point?
No.
Yeah, my name is Case. My office is right here. You can see it. If anyone can't come to the exercise sessions but has some questions, feel free to send me an email or you can drop by, usually here.
Crazy, he did it again.
Yeah, there's a lot of people. But, hopefully we can make it.
All right, he's also excited, you can tell. Now, why do we do this? So this is introduction and motivation. For quantum field theory. And so I first asked, why do we do this? Why care about quantum? You can read this from the back, please let me know. And I mean, I can get 2 lines on each floor, it's gonna be a lot of writing, but I'd rather write more often than not read it. So that's a mix of quantum. We have something quantum theory. And you have something here, field theory. You have a question mark? Okay. And so let's ask, why do we do, or recall, why do we do quantum theory? Well, what does it mean? Our classical world, where we have experience, is you're smooth and continuous. So you have variables that represent physical quantities, which can take usually any real number. Maybe it has to be positive or something, but it's a set out of the real numbers. But then if you look into the microscopic world, atoms say, there your electron cannot take any energy that it wants. So not any real number is allowed. If it was, it would go to 0 and then everything would be unstable and collapse basically. So in the quantum world, you see those gaps. They're also here, but they're so small, these gaps between the allowed values of energies, that you think of it as a real number and really continuous. So it's just a matter of life that the world is quantized. So that's this quantum thing. Variables, so we have here on this side, we have the variables that represent physical objects are random variables. That's your formalism. So you have a random variable. For example, x for the position. You have the momentum, you have the energy, stuff like this. And then you have probabilities. Probability amplitude, say. This sign thing, that's the probability amplitude of finding a certain x. So x is the position of particle, and that's the amplitude of the probability to find the x at find the particle at this given x. So you just square it, then you get from the amplitude to the probability density, and then you can. I'm just as a gentle introduction. And you can have for this thing the momentum space, probability density, and then you can have the other densities for n represents the allowed, labels the allowed energies. So you know, and then you can compute things like expectation values. It's this thing. So you integrate your probability, which is the square of this psi. And this can be complex, so I take the absolute value of x, and it's your rotation value, You can have uncertainties. Delta x, let's be square root of the expectation value of x squared minus x is the particular squared. So all of this, but writing this down is not in vain because we'll do quantum field theory and you'll see all of this. We'll compute these things if we take them. So that's the quantum world. And that's a matter of fact. Oh, I forgot something. I forgot to bring something. Because this is so important that you have to wait for 1 minute.
Okay.
So good. Oops. What in the minute was it? So the other side is now why field theory. If you think of Coulomb's law or Newton's law for attraction of masses, then there's no time in it. In this law, the mass times mass over r squared. You change the distance, then you change the force. So one moves closer to the other, distance changes, force here is instantly different. That's action at a distance. And that's another fact of life that doesn't happen. And I have this wonderful toy, a slinky. And I shouldn't have said anything about fields and action as a distance. And then ask you, so I spoiled it already. First I forgot it and then I spoiled it. I'm going to drop this now. And you're supposed to look at the bottom end. And you're supposed to predict what happens to the bottom end when I let go. Try it. Yeah.
Well, first of all, it's not going to change much. And then finally, it collapses.
Probably. How long is it going to take? So he says it's not going to move much. It's just wiggling like it because I can hold it still. But then it eventually will go, I suppose. But when? You.
I'll let him.
No,
It's really experiment, right? First experiment in quantum field theory. 3, 2, 1. You saw it? It's wonderful. Did you see it in the back? Well, you want to tell them what happened? When did the bottom thing move?
Yeah, the top came first to the bottom and then collectively.
Yeah, exactly. So it waited until the top came there and then it moved on. So that's my point. Things don't have effect here when the cause is there. It just needs a little bit of time to propagate. And how do we model this? Not random. We have a field, a dynamical field, a field that is time dependent, and there's some interaction, some change, and then it propagates. So you have a wave. You can really look at this and use this as a tool to figure out what equations to write. Like you have a wave equation, and things propagate, and then you have it there, and you end up with field theory, right? So you have. How do I write this? So in the lecture note that I pointed to, you'll have it in all detail. Here I'll just be sketchy and say no action at a distance. So whatever force information levels at finite speed, and in our world it happens to be the speed of light. for, electromagnetic interactions and gravitational interactions, both the same thing. So you have this speed limit. Okay, so speed limit, the finite speed is called c. And then this gives you more trouble because if there's something propagating with this universal velocity c, and your friend follows that thing, then he naively will see that first object go slower than we saw it, than we are seeing it. Or if he doesn't follow it, goes the opposite, then it suddenly will be even faster. And that's not a speed limit. Well, we could probably live with slower, in the sense of giving a ticket, but this is supposed to be universal, and everything, it doesn't go faster or slower, it's just this. So, what does this result in special relativity? With all the stuff, Lorentz contractions and time dilation and these things. So we have, as soon as we say this, and that was the proof, we say special relativity. And with special relativity comes my favorite, or everybody's favorite formula, m is equal to mc squared, the equivalent of mass and energy. Is what's like the energy for one is mass for the other. And that's that side. And both is fine. And now the question is, why do we want to combine both? I don't know if it's really the question why, because this is our world, right? We said we observe this, and now you probably have experiments or things that require both things. So we need to combine the two. But the question is more how and what will it lead to? So there are two ways. We can quantize the field theory side. And that's a word, quantize field theory. So make it discrete. Instead of having an electromagnetic field, for example, that's our field theory, you have lumps of energy called, in electromagnetism, the lumps of energy, photons. So you will probably, you don't see the photon really in classical electromagnetics, right? You just have E and B, but if you quantize, you'll probably see the photon. In quantum mechanics, they tell you about it, but we don't really necessarily see this thing. So, good. And then we can have experiments, or a mathematical description for experiments for individual photons. We could also do the other thing. We can relativize quantum mechanics, and that's not a word. I made this up, but I thought it's funny because we quantize field theory, and we really should be try to make this compatible with relativity, but that's too long. So we relativize. Don't repeat this because of the word quantum theory. Why would we do this? Well, it really means to add the speed limit to it. And particles at the microscopic level can go really, really fast. So why? That's very sketchy, but still everybody does it. So you have delta x times delta p is larger or equal h bar half. So the product of these uncertainties should be larger than some minimum. So you can't have both zero. You can even have 1, 0. And if you're looking at small things, you have probably small uncertainties. It's roughly the size of yours. So it's small. If that's small, this has to be large, a large momentum if you think at least classically, I mean, non-relativity, like Newtonian mechanics means a large speed. So it should at least think about whether P is equal to mv still makes any sense. So P gets large. So things are really fast. So you want to, so we'll get the speed limit here. And we get this, the particle production. So you have studied, let's assume you have studied this thing, you talked about the microscopic world with all the probabilities and the expectations and all this stuff, and then separate course you have studied field theory because you didn't want the action at the distance and you found special relativity and this. And now we want to put both things together in this semester. And what you get is for example, many more things, the photon, and this business of particle production. That you get quantum field theory by quantizing field theory is inevitable, right? Because it says the word by definition. If I quantize field theory, I end up with quantum field theory. It's not obvious that you get also quantum field theory by relativizing, that's another word, quantum theory. But you do. And that will be the topic of the first two chapters. So this week and a little bit of next week. That when we try to make what we know of quantum theory relativistic, we really have to go the full step to quantum field theory. This will then also answer the question, what is more fundamental, the wave or the particle? Because here you could think, okay, quantum theory I liked, I understood, here I now end up with, so there were the electrons, and here are the photons, other particles. So you, at some point you might think, oh, the particles are the fundamental objects. And then if I have many photons, I have my field, but really it's the fundamental part, the fundamental is the particle, you could think. But we'll see, actually it's the other way. So fundamentally you have the field, that's why it's the source. And you need this because you need to produce particles kind of continuously, even with undetermined particle number, and that you can nicely do with the amplitude of the wave. So you just grow your wave a little bit more in there. And all right. So what we're going to do the next week? We'll try to make quantum theory relativist. But before, I'll give you an overview what the long-term goals and what can you do at the end of the course. At the end of the course, you will be able to calculate the probabilities for scattering events between individual electrons and photons. Or if you won't be able to calculate them, you'll at least understand how they are calculated. The calculations are complicated and long and tedious and many indices and many signs and many sources of error, but you'll know how it's done in principle for the simplest courses. So you go, let's write it down, go, and then we see if we ended up there. The goal will be to compute the probabilities many for scattering events of individual electrons. Okay, write it down. Electrons, positrons, photons. for example, there's this thing that's called Müller scattering. It's a full name. And this is an electron beats another electron, and they repel each other like this. So here's an electron, and there's an electron, and they go like that. Minus, they fly in here. And you'll be able to tell me what's the probability that this guy makes this angle theta relative to its original trajectory. Wonderful, right? That's why you came, I hope. Is that why you came? Yes. Right, so then good for you. These are the kind of questions. Or you have Baba scattering. That's E plus and E minus. Looks the same, except for they attract, so it goes like that. They come towards each other and then like Earth and Moon. Not really, because they are found comet and go like that. You'll be able to draw Feynman diagrams, which represent these processes in a sort of pictorial fashion, but which is, however, one-to-one to a mathematical expression. So for example, here in this first thing, you draw this. There's an electron coming in and an electron coming in, and so time is this, and then here it sends a photon. Electrons send photons, virtual photons all the time, and then this one feels it and makes a turn. And then this goes there. So you have your electron coming in, and after time, this is a Feynman diagram, and you'll be able to draw all these things and translate them into expressions. You've seen a Feynman diagram before? Yeah. Exactly, there it is. No, that's stupid. Yeah, before, I said before. I'm trying. I also want to write down the steps to this goal. That's the goal. And what are the steps? It's going to be like 14 weeks, 28 lectures, 14 problem sets, maybe 13. So let's see that we can what steps, the overview. We'll start from quantum mechanics to QFT today, tomorrow, next Wednesday. Then we'll do some classical. We need to do here this field theory side a little bit. We do classical the relativistic. Field. How's the handwriting? I got this. It's bad still, right? I'm trying too fast. I go too fast. Wow, don't say that.
No, I mean, so far.
It's bad, and then I'll be better. So once we have this, we'll talk about symmetries. This chart, this is sort of the connection to the real world. You can write on many equations, but you need to know what is one problem we'll have to understand what's our particle. We write a formula, and okay, where's the particle? What's a particle? A particle is something with certain properties, and they come essentially from the symmetries. How do you transform under translations? Oh, you have a momentum, and then okay. So symmetry is going to be important. Then we go from classical to quantum. We quantize three scalar, scalar, and vector fields. So here, we'll talk about what a scalar, spinor, and a vector is. And then we come to we'll soon be introducing interactions. There's one more, and then we go interactions. So here we're still free. You can do two things. In books, I think more often than not, you find first everything with scalars, spinless objects, classical quantization interactions, and all to the end. And then you do the same. Okay, now I need to introduce a spin, and have my spinners, and you go through the whole thing, and that's one way of doing it. But and then usually they say, if you do the spinners, we'll do the same as for the case of the scalars with these modifications. But that's weeks after, and nobody will remember, even me. What did I say? You know, and so this idea is now to intertwine. So we go step by step. First, we do everything with the scalars, and then we learn what scalar is. Then what is a spinor, and then also we have the contrast with the scalar, so we appreciate more what the scalar is. And you know, if you just talk about a scalar is something that doesn't transform. Okay, thank you. If you want to know how would it look like if it did transform, maybe that's the idea. I hope it's a good choice, but that is the choice I'm making. So we'll it's got on the sort of drawback, maybe on the flip side, it's going to take a while until we do quantum and interactions, but you know, it's going to be fast, of course, anyway. So we'll do this, all the different types. And here, just the keywords, we have to talk about Green's functions. Propagators to certain kinds of Green's functions. You have correlation functions as well. You have a Wick theorem. Just some keywords, and then we finally get to interactions, and we have our S matrix. S is for scheduling. That sounds like what we want to do. Matrix, and then there's something called LSC reduction, which connects the Green's functions to the S matrix, and then we're really good. That could be the end, but there's a different way of quantizing. I haven't said how I was going to quantize. It's canonical quantization, but there's a different way of doing it. It's called path integral quantization, and Modulbeschreibung wants us to talk about that too. So we do path integral quantization. That's a really nice and fancy formalism. That's not actually necessary. You could do everything with the stuff you've done up to there. And finally, we'll touch up on denormalization. Which will also be sprinkled in a little bit there. It's also about how to connect your formulas to the real world. We'll write M for mass, and think that's the particle's mass, and we'll realize it's not. It's just a constant, and we have to connect this to the actual mass of the particle, which will be different from our symbol M by infinity, finally, and then we call it denormalization. This is very exciting. Often it sounds scary because you have divergent integrals and it's technically complicated, but physically it makes a lot of sense. Even if you haven't understood, if you don't know any of this, you haven't understood because I haven't really explained anything, but these are the words. This is the plan, so you know where we're going. Do you have any wishes or so, or hopes or concerns or for this journey? Yes, we can start the journey. Chapter or the section on relativistic quantum mechanics, and to be honest, this is going to fail. I anticipated we will end up with the quantum computer. So this attempt is going to fail. And I could cut it out of the course, if it fails, but it's also what has happened historically. It's the first step in trying to combine quantum mechanics and relativity, and that's the step that they went. They didn't go, oh, okay, let's do field. So we'll go this way, and it's interesting to see what happens and why it fails and so on. But to be honest, from the start, it's going to fail. To do this, I first start non-relativistic. Looking anyway, non-relativistic. QM as a reminder. How to get the Schrödinger? How do you get the Schrödinger equation? I want people to come and do the first row. If I bother you all the time, then you're not going to come back again. How do you get the Schrödinger equation?
From with kinetic energy.
Right. Very good. I write it as not 1/2 mv squared. I write it with the momentum. I write this thing. It's called the energy momentum relation, or sometimes dispersion relation. And then you do what? Okay, let's do whatever. Let's do potential energy. If this thing moves around, you can change, and then
Use operators instead of.
right. And sometimes you call this the correspondence principle. Correspondence principle, and that is the energy is replaced by I h bar time derivative. P is replaced by minus I h bar space derivative. What do you mean derivative? Where is this supposed to act on? Just a poor little derivative doesn't have anything to act on.
Wave function.
You have to multiply this by the void. And so you go from here to there by replacing it. So we have I h bar dt wave function of x and t equals p squared. You know all this. I have first second derivative psi of t and x plus b of x and c t and x. All right. Is this a derivation of Schrödinger's equation? Why not?
He just moved stuff up. But
They just made it up, yeah.
Or like showing how you could get it, but I want to say it's the derivation.
Yeah, and that's
Physical
important.
motivation.
Yeah, exactly. So you have this world microscopically that you can't really touch and see so easily, except for complicated experiments that you don't see, you don't have any intuition. How am I on Earth supposed to come up with an equation describing this, right? So you have your discrete energies, the levels in your hydrogen atom or something. You need an equation that produces discrete numbers. This is going really slowly. So waves Schrödinger said the thing with the waves. If you have waves and then you try to squeeze waves into certain intervals or for the atom around the circumference, then you get some discrete options, right? So because you can squeeze 1 or 2 or 3, but just a discrete number. So that's kind of the idea to come up with an equation like this. But that's just a guess, because how else would you start? So you're guided from this, because if you, this is more general, supposed to be more general. It's supposed to be supposed to include the classical physics. So there needs to be some relation. But from there to there, I don't know, you could call this canonical quantization. Really, technically, it means slightly, it's a more specific term, but that is sort of like the canonical is, if you wanted to quantize a system, your own means, you pick your potential, whatever you can afford, what kind of force you can afford, then you want to make a quantum theory for your system and you have no idea, then you go that route, that canonical quantization, that one that usually works, that everybody does, and apply it here, and you do this. It's not a derivation, but this is, and it's kind of fantastic that it works, because if it always worked, it really meant that the macroscopic physics implies the microscopic physics. That's just crazy. I think there can be more underlying than what you see when you average, and that's what happens. So when we do things here, we are really experimenting with equations. I wanted to make this clear from the start. All of this is still work in progress, right? All of those infinities, all the difficulties we encounter, they trouble everybody. And we're not sure that this is the final framework. People work on modifying it. You see, this canonical quantization doesn't work for gravity. You need something else. So I might tell you something that will be useless eventually. Won't be now, but eventually. What am I saying? I want to say that we are trying to come up with something that works here, but it's not a derivation, and we are motivated in this path that we're giving is called this canonical quantization, and replaces these things. Okay. Now, since we were given this is a guideline how to get a quantum mechanical equation, let's do this for the relativistic dispersion relation. Yeah, we are trying to invent relativistic quantum mechanics. We have no idea. We don't even bother doing experiments. We'll just do this here on the blackboard. We'll replace this equation by the relativistic dispersion relation. That is, oh, sorry. Blue shirt, blue sweater.
Klein-Gordon equation?
No, the relation between energy and momentum relativistically.
Energy squared is p squared 2m plus p squared plus m squared c over c hoch 4.
Okay, m squared c to the 4th, right? That's the thing that you might or might not remember. E is equal to p. This factor c is like for the photons, right? The dispersion relation for photons is energy is c times momentum. Well, I don't know why I'm writing this. So you have the p and the e of p, and that's the photon. But here we have a rest mass. So if there's no momentum, it's 0, then we still have some energy. E equals to mc squared. We have to all square it. We have to sort of like Pythagorean, well, we add the momentum part and the rest mass, and then the whole thing looks like this. So here's the mass. And that's the energy of the particle for a given momentum. So if you have your P, then you know what the energy is. And you need the mass. This thing is, by the way, it's not important now, but it will be later. It's called the mass shell. Looks like does it look like a shell? I don't know. If the P was a vector and we had a three-dimensional plot, then we could do at least two components of P. Then we had this bowl, mass bowl, or the mass shell. Okay, so that's the equation. And now, why not applying this correspondence principle? Then we get here minus, I guess, I squared, h bar squared, t squared, on some wave function t psi of t and x, plus minus again, equals, and then minus from the I squared, c squared, h bar squared, t x squared, psi, t and x, plus n squared c to the fourth psi, x and t. So that's our equation. I could put a box, but I was gonna make it a little prettier by dividing this equation by minus 1 over c bar, c squared h bar squared. And this goes away. Here we have 1 over c squared dt squared psi of t and x. This goes all the way. That's on the right hand side. If I push it to the left hand side, I get a minus sign. So dx squared psi of t and x. And this loses two c's, gets an h bar underneath, has a minus sign on the other side, will be plus. So plus m squared c squared h bar squared psi of t and x equals 0. Okay, two more steps. I'll factor the psi. 1 over c squared dt squared minus the x squared plus m squared c squared h bar squared, and then everything acting on that wave function. And this now, I'm sure it said it, is the Klein-Gordon equation. In fact, Schrödinger had this equation first because he knew relativity and he thought, I'll do it right from the start. I'm not bothering with Newtonian physics. I'll do this. But then he ended up with trouble, which I'll show you now and tomorrow. And then he discarded it and then ended up with this thing down there. Has less trouble. There's a notation where you write this object here short as box. Doesn't make it better, shorter, so we have equation box plus m squared c squared over h bar squared psi of t and x. And you'll always have to go back to this. What does it actually mean, that box? You need to go and look. Because it could also, where the signs, where the c's. Maybe someone has defined it as minus box. Crazy. Maybe the c there. So you'll have to go back, but this is not shorter. I'll tell you how this is related to the scalar product of four vectors and what a four vector is and what the metric is later. This is, if you don't, this is it's called the inversion, right? The Lambert operator. And it is the scalar product of two four derivatives. We'll discuss that. That's the equation. And now the trouble, I guess. The first, oh, the potential, you forgot the potential. Did I forget the potential? Somebody forgot the potential. We forgot even more. So this thing has the problem that you have two time derivatives. That's the difference structurally from Schrödinger's equation, which is just one time derivative, which means if you want to solve it and find a special solution, you have to supply initial conditions, and they're very different. Here, you just need the wave function at an initial time, just the wave function, that's it. Here, you need sort of both. You need the shape and the speed of your wave at first. It makes a difference. A big difference whether you have to supply both or just one. In quantum mechanics, so in classical mechanics, for a single particle, you have to say where it is initially and what's the speed. You can't say what is the initial acceleration, for example. It's not up to you to choose. It depends on what the force is. If you change the force, you might be able to accommodate different accelerations, but it's not an independent thing that you can choose. If your system is given by given a potential or a force, then that's what it is. You have your acceleration. So you can choose where you start and how fast you start. In quantum mechanics, you have the same thing. You can set the system so that you can say where is my particle or where its probability distribution on what's the momentum distribution in the beginning, and that's encoded because of the complex number in the phase. So basically, the amplitude of this modules of this complex number is where is the particle, and the phase of this complex number is how fast. Roughly speaking, not precisely. The phase isn't literally the speed, but the information that can be stored there. So it's enough to have just the complex psi of T and X as an initial condition. And now, suddenly we have to give much more initial data just because we went relativistic. Strange. We could do something else. We could take the square root here. Another idea. Alternatively, we could have said we take the square root. It's still the dispersion relation. And as I said, we're not deriving quantum physics. We are just guessing it. And now we can apply the correspondence principle to this thing. And then we have from here, we would have minus plus I h squared t squared psi of t and x. And then we have square root c squared minus c squared h squared x squared plus n squared c to the 4 and all of this. That just looks ugly. What does it even mean? It means that you have to think of this square root as its in terms of its Taylor expansion. Because I mean, how else would this? So you can Taylor the square root. This is small. So you divide by this 1 plus something small. You expand and you get a series in these terms, and that is disgusting. If you don't like to expand it here, you can also do it here, right? So this is equal to mc squared. We know that. But if you do it, you set p to 0, then you get this term. And the next one is, funnily, p squared over 2m. That is Schrödinger, the first term. We didn't have the rest mass, we don't need this, so it is. And then goes on minus something like this. I'm not sure if I reached. Oh, I wrote it down, but then I knew I wouldn't. M to the 3 c squared and plus. So you can expand it here, up here. And then reach the correspondence principle for all these p's. So you get higher and higher derivatives in x. So that's the second derivative, like here, and then get the fourth, and so on. So this means infinitely many x derivatives. That's also not cool. Because if you want to know, like, what's the change in time of your wave function at a certain x0, say. It's written here. What is it? It is the right-hand side. But the right-hand side is infinitely many derivatives on this thing. So if you have so many derivatives, you need to know all the value, the slope, the curvature, and all the different derivatives. And that is equivalent to knowing what the function looks far away. Because if you know all of them, then you can do Taylor expansion backwards, basically, and then you know what it's there. So that is essentially a non-local equation. The change of psi at some location depends on the wave function everywhere else.
But like you don't need to like know the function far away. Like you can actually go as close as possible as you want, and you still could like get all of these derivatives. Like, isn't this still kind of sort of local enough?
If you truncated this somewhere here at a finite point, yes, then it's local and you need all these terms. But the real problem comes when this is the infinite series, then you need to know everything. And assuming this is an analytic function, it really means you know the function. You have to know the whole function everywhere. You have to give all these derivatives. And that's just I wish to I had a line there, so this is a non-local equation, and that's also bad. That's why this thing doesn't get a name, and that one is the Klein-Gordon equation. Someone forgot for me to add the potential. So let's pick the first approach, but with the potential. So Klein-Gordon with potential. This is, so what do? We have to add. So the energy, this is the total energy, is equal to the kinetic energy, c squared p squared plus m squared c to the 4, and now comes plus the potential. Doesn't make any sense to add it here, right? I can't just add b squared or b. B doesn't make any sense. Then the Einheitenpolizei, what that's in English, the unit police comes, so I do the squared, but that still doesn't make any sense. Why would we add them squared? Kinetic plus potential energy is just added linearly. So that doesn't make any sense. So I have to take the square root, then add it, and then square it. Because we like the squared version better. So b comes here, e minus b of x, then we square it to isolate it. If you didn't isolate it, wouldn't get rid of my square root. So I have this. And now the correspondence principle, and that is then I h bar e2 minus v of x squared psi of 2nx equals minus c squared h bar squared dx squared psi of 3nx plus m squared c to the 4th psi of 2nx. I actually like this. Shouldn't be right, but anyhow. I like this version for practical purposes, so not to multiply out this square, keep it like this. But you could also multiply it out and do the same steps that brought us from here where there wasn't the potential to this, and then you would end up, and I'll just give you the answer because it's kind of boring. It's written in the notes. It is this equation, right? It is this psi of t of x equals b of x squared over c squared h bar squared psi T n x minus two v of x over c squared h bar squared I h bar dt psi of t and x. So I reused it from the previous blackboard. It happened to be at the right place, but no, this doesn't make any sense. So from there, you get this with the same, well, the same steps. And here you see the Klein-Gordon part on the left-hand side, and then the right-hand side vanishes if there's no potential, and you have basically your free Klein-Gordon particle, and with the potential you have this right-hand side. There's Max. Hello, Max. Can you hear us?
I think he's in the doctor's office. So he's
Oh, he can't talk.
So he can't really, yes.
Okay, I wanted to know how the audio really is, but I'll figure out, it doesn't matter, I'll figure out later. It's too bad. If he says it's really bad, then I'll just be sad for the rest of the day. And I can't do anything about it.
It wasn't right.
He would have left. He has left, see? Right, so this is our equation, and now we have, so we said that there's a little bit of trouble with the second initial condition. Why do we have to give psi dot, the time derivative as an initial value? And what is the interpretation of this psi, the Klein-Gordon psi? Like in the homework, I really make a difference between the Schrödinger psi, that is a solution of this equation. So if you write this equation, then that psi is the Schrödinger psi s. And if you talk about the relativistic theory, then you have this equation, and there's also a psi, but that's of course not the same psi. It's a different, it has to be, it's also a different equation. The equation is very different. So it's a different function. Don't confuse the two. I guess you wouldn't, because but there's a potential that someone else would. There's psi and there's plus not the same thing. So we have really two, but that's also clumsy to write with this index. Anyway, there's the two different things. And now I want to know what is the interpretation of this. You know what the interpretation of this thing is? It is the amplitude for the probability of finding the particle at a certain t at a certain time around x, location x. So we have this row of t and x, Schrödinger say. This is just psi Schrödinger t and x squared, or waste some time, complex conjugate times this. So this is the probability density of finding the particle at time t, let's say near x. It really should be in an infinitesimal interval. So the probability, what's the density at time t? And probability density has which unit? What's the unit of the probability density? Does it have a unit like kilograms? What?
Doesn't have one, right?
Right?
Doesn't have one?
Ha. This one.
1 over, well, length cube, or
Right. 1 over the unit of the random variable that we're talking about. We're talking about the random variable x. X is the length. So this thing, rho s, has units 1 over length. Why? Because the probability p, I spaced, the probability p, Schrödinger can go, I guess. Can he? No, not yet. So the probability rather than the probability density. I didn't have a good name. Someone else told me in math they use p with a double line, so this is the probability of finding the particle. This is integral of the density. So if you don't want to you don't need to integrate, then it's the probability in this interval. So that's the probability of finding the particle. The same words except for density. The probability of finding the particle at time t in an infinitesimal interval of length delta x located at x. That's what this thing is. And this is a length, and this is a probability Cantor unit, so this would be the inverse length. That's why the wave function is the square root of the inverse length. Good. And if I integrate the whole thing, I get 1. So the integral over rho, the x from everywhere to everywhere, I want 1 because I want to find my particle somewhere. I lose it, but it must be somewhere. And if I search everywhere, I'll find it. So that's just a note. I was talking about this here. This is just that's the interpretation. And that makes sense, first of all, because it was all of this was invented for this purpose. You had like the double slit experiment, and you see there's interference. And how do you model interference? Oh, by adding waves, thinking of them as amplitudes that you then square, you have interference and all that. So that's how this squaring came about, and the probability amplitude giving you then I squared the probability density and all of this. So it was constructed this way. So that this is basically because we wanted it. But it also makes sense for a different reason. The Schrödinger equation, I don't know, I'm just saying, I guess, that it's consistent. This rho is it's locally conserved, it's a local conserved charge. So you have a continuity equation. So here is where I want to go, continuity equation. So the continuity equation says if some stuff diminishes at a certain location, there needs to be a current that moves it away from there. It can't just evaporate or disappear, just go without anything. If something changes in terms of its amount, becomes less, it has to move to neighboring places. And if it becomes more, then something has to flow there. So the change of rho needs to be accompanied by a change of a current. So this is some sort of this rho is, I mean, you can talk about continuity equation in different contexts, could be charge, could be whatever you want to have. But this is the stuff density. I just write density. Density of something. And this is the current of that something. So if this is whatever, gummy bears per meter, then this is gummy bears per second. What is your favorite object that you want to conserve locally? Let's say Coulomb, why not charge? Yeah. So if this is Coulomb per, so you have your line there and you have a charge sitting there. So this is your Coulomb, but it's Coulomb per length. And that changes. So this object is Coulomb per length and time. This is per length here, then this can only be Coulomb per time. So it's how much charge per second moves to the right. If this is positive, J is positive, moves to the right. If that object is negative, so your stuff gets less at some point, so it's negative, and this has to be negative with the minus sign, without the minus sign, this has to be. But the whole thing has to be negative, so say this is negative, and that is negative, this is equal. It means this thing is positive. So it means that the current further to the right has to be larger. So it's all flowing this way, but it gets larger there. So more is moved away than through that location. So that's why it decreases there. Fine, now we figure out the sign. This is your continuity equation. And it actually is implied by Schrödinger's equation for this density. So this is the density of something that is locally conserved. And if you solve the first problem on the problem set, you will have shown that the corresponding current J is equal to minus IH bar 2M. And then psi star. I need to write TNS now. And then it's the spatial derivative psi minus dx psi star psi. Cool. I assume that you have seen this many times in the quantum mechanics course. This is the normal current, right? So this is the momentum, and then you divide. So this is where is my H bar? It's my H bar in the right place. One have I? Oh, sorry. Yeah. These all together. This is the momentum. You have two terms. Two goes away. Momentum divided by mass is velocity. So what's written here is basically the density times velocity, and that's the current. And now this equation is the Schrödinger's equation implies the continuity equation with this charge and this. So if your particle moves, the probability kind of moves, but it's conserved in total. Do I need to say this while I'm filling my time? Yeah. So the total charge, or the total amount of something, I like to call it charge. The total charge is conserved. You see it like this. You go d by dt of the integral of rho of t and x dx. So this is all there is. Charge in the overall space. You take the time period, see if it changes. Then you move derivative into the integral because this is the spatial and that's the time. So then you differentiate the charge with respect to time first. Now the function of x, and you integrate this thing. Now we use our equation here. So dt of rho is minus dx of j. It is minus integral dx of j dx. And now you have an integral over a derivative, which is really just the function that you differentiate, evaluate it here and there. With the minus sign, I'll move it around, so I'll do the lower limit first. So we have k at time t. So we want to see the changes. Minus infinity minus j t plus. So if, see, this is our world. here's infinity, and there is constant that ends the world. And if there's an eddy current leaking out of our world, at infinity, here or there, or something coming in, and the whole thing is conserved. So this is equal to 0 because this and this is 0. Yeah, you know, if nothing leaks. Leaks. Energy. Everything is falling off, so when we come close to infinity, we'll just shut it all down. It's a bit hard if you partial wave, you know, these different momentum, you know all these problems. But anyway, this is the honest answer. If there's nothing at infinity, then this is conserved. If there's something at infinity, it's not conserved. Now you can ask the same, we should ask, that's why I'm bringing this up. We should ask the same thing for a Klein-Gordon equation. Is there a conserved density? Is there any continuity equation like this? How do these things look like? It will be very different because our equation is very different. We have the second derivative here, right? Where does this come from? So we want dx of j to be somehow equal dt of rho. So a time derivative here is the first order time derivative of the psi should be somehow equal to an dx, and then there's another dx. And that's what the Schrödinger equation had. It had one time derivative and two x derivatives. Now our Klein-Gordon equation has two time derivatives, so that's probably going to look very different. And it does. And I'm just going to give you the expressions, and then it's the instructed exercise to show for this relativistic case with Klein-Gordon that they also satisfy the Klein equation. So Klein-Gordon. Then we have rho Klein-Gordon. Next, this is different now. I h bar over 2m, and now you need the time derivative. Minus d2 sine. But that's only the first term. There's also the potential stuff. So we get minus v of x over m v squared psi star psi. There you go. And the j, Klein-Gordon quantity, very same. So it's the exact same expression, psi star dx psi minus psi minus dx psi star psi. Done. Now this is of course the Klein-Gordon psi. Here's the Klein-Gordon psi, and here was the Schrödinger psi, but it's the same formula expression. Or in terms of the V. In terms of the V. And now we have this. Now we have to make sense out of that. It was obvious. I'm looking here that this quantity is positive. Psi can be complex, but since this is the complex conjugate, this is the absolute value squared, and that is necessarily positive or zero. It cannot ever be negative. So the probability interpretation makes sense. If we had a negative rho, it wouldn't make any sense because then what does it mean? That the probability of finding the particle here, the density is minus now. Either it's there or not, but not less than. Like, is it very unlikely to be, very unlikely means a small number, not a negative number. So that doesn't make any sense. And luckily here it's always positive, but here it isn't. This can be negative. In particular here, you know, that's positive number. Whatever this is, just crank up your potential. you'll end up with something negative. You have to think about it. This is probably positive here, and then this is the complex conjugate of this, but it's a negative sign, so no, I guess this can also be negative, right? It's just a number, it's just a real, it just means it's a real number. Yeah. So definitely, if not for this reason, this term we'll be able to make that negative. So we're in trouble. So yeah, on that sad note, we are trying to make quantum mechanics relativistically invariant. Come up with some fundamental equation that describes some quantum theory, but implements the speed limit. And maybe particle production if you want, or something like that. Not going there. Just the speed limit for now. And the first thing that people came up with, that we come up with, is use the relativistic dispersion relation, use the correspondence principle, because that's our guiding principle in the non-relativistic case. It worked there, why not here? Try it. And then this is where we are at the moment. We have this continuity equation, we have some density, but it doesn't have a probability interpretation. It cannot be the probability density of something, of finding the particle somewhere. And the question is there any sensible, of course, interpretation of rho kg? Well, this, I should have said, I said it in words, but maybe if you write it down, well, of course, it is, but this can be negative, yeah? Just by keep this in mind, so it can be negative. Can be negative. All right. So that's why we are asking that question. And that will be discussed tomorrow. Just to make you come back. Do you have any questions or comments or wishes? Max?
But check, the sound is fine.
Yes, oh, wonderful. Thank you for checking.
I think Max got an issue.
Well, then, digest this for now, and then I might see you tomorrow. Thank you very much for today.
Aber das ist war der Horror. Ja, er hat mich irgendwie von uns und ich habe nur seine Videos geguckt und habe es genau so ja.
Nice to see you.
Das war mal